Okay, so here we are with lesson number 5 in our unit on energy and momentum. And we're talking today about different types of energy. We've looked at work in a previous lesson, and we're going to build on that concept and now talk about how work really is the process of transferring energy from the force to the object in the form of motion. Okay? And one of the first things that we see is the kinetic energy work theorem, which tells us that if we sum up all the different types of work that are being done on an object, that will change the kinetic energy of the object. Okay, and we've seen previously in different courses that kinetic energy is given by the expression EK equals 1/2 mv squared. And if you want to see a derivation of this, take a look at your textbook, and it will most certainly give you that. But we want to move right into what kinetic energy is and what it's all about, because it's the energy that's associated with the motion of an object. So whenever an object is in motion, we say it possesses kinetic energy. So let's take a look at how a very, very straightforward example of how we might calculate the kinetic energy, knowing that kinetic energy is defined as 1/2 times the mass times the velocity squared. So here we have a 2 kilogram mass, and it has a 3-dimensional velocity, 2I hat minus 3J hat plus 6K hat. And the first thing that we can write, of course, is that mass is equal to 2 kilograms. And we need to be able to find the velocity. We have it in this form, 2I hat minus 3J hat plus 6K hat. But of course, right away we know that if kinetic energy is equal to 1/2 mv squared, then all of a sudden, somehow, we have to take this v, we have to find v squared. And the way that we do that is that we say, okay, well, v squared is nothing other than the dot product of v and v. Okay, so that's what v squared is. It's v dotted with itself. And the way that we do this is we take the dot product. So we've got 2, -3, and 6. And we're going to dot that with itself, 2, -3, and 6. And of course we remember that we take I, and J, and K, and we multiply those and then add them. So we've got 2 times 2, right? 2 times 2, plus we've got -3 times -3, plus we've got 6 times 6. And if we go through and we multiply each of these out, 4 plus 9 plus 36, we end up with 49. And this is v squared. And so now we can turn our attention to solving the kinetic energy, because we know all the different parts. And we can say this is equal to 1/2 times 2 kilograms times 49, and we get 49 joules. And so this would be the kinetic energy of this object. This is a very straightforward example but it gives us a good introduction. Most of the time, we're not going to see a three-dimensional object, especially in grade 12 physics in Ontario. Most of the time, we're looking in 2 dimensions. And so a three-dimensional velocity, this is just a small extension, and we can do it, so we may as well. But most of the time, we're going to see objects that are moving in 2 dimensions. And so, of course, the k-hat may or may not be present, but it's there, and we can deal with it if we want. Potential energy is energy that's stored in a system because of some force. And it's available to do work, although it may not be doing work right now. Potential energy takes many forms. Okay? And we're going to mainly concentrate on 2 specific types in grade 12, gravitational potential energy and elastic potential energy. And so that's what we're going to look at. Of course, we did investigate gravitational last year, and now this elastic potential energy, this is our new addition for grade 12. So when we talk about gravitational potential energy, this is energy that's stored in an object because of its position in Earth's gravitational field. So we always, can set a reference point for our base height, which is 0, and if we raise some object to some height h, it will then possess, in a gravitational field, it will then possess gravitational potential energy. And there's a really, really quick derivation. If we start with work is equal to force, the dot product of force and displacement, we know that when we're talking about the force, in this case, we're looking at the force of gravity. And we're taking the dot product with the displacement, which is simply the height that we're going to give the object. And so at any point in a gravitational field, we've got mgh. And we arrive at our expression for gravitational potential energy is equal to mgh. And so very, very simple, straightforward definition, but this is gravitational potential energy. And so we're going to work with this now. And this is, of course, very much a review for most of you. And we'll take a look at a straightforward example. A basketball player at the free throw line shoots the ball at 7.2 meters per second from 2.21 meters above the ground. The hoop is 3.05 meters above the ground. How much potential energy does the ball gain as it leaves the player's hand going from 2.21 and travels to the basket, which is 3.05? Okay, so we start with our initial position. Right, so the ball initially has a height of 2.21, and if you were to Google a regulation basketball and its mass, you would find that it's 624 grams. It's a regulation NBA basketball, 0.624 kilograms. We know the initial height is 2.21 meters above the ground. And so we can say that initially this ball has a gravitational potential energy of mgh1, and we get 0.624 times 9.8 times 2.21. If we do the math, punch this into our calculator, we get 13.5 joules of energy. Okay, so that's the initial state. And because we want to know how much potential energy the ball gains, we should also look at the final state of the ball. The mass, of course, hasn't changed. It's still 0.624 kilograms. but we have a new height. We're now at 3.05 meters above the ground. And so EG is equal to mgh2 at this point. And we punch this into our calculator, 0.624 times 9.8 times 3.05, and we arrive at 18.7 joules of energy. So indeed, we have gained potential energy, and that gain, we can say, is delta EG, which is EG2 minus EG1. So our final gravitational potential minus our initial. And in this case, we had 18.7 joules minus the initial 13.5 joules. And we get an increase of 5.2 joules. Okay, so we can conclude saying, therefore, the ball gains 5.2 joules of potential energy. And there we have it. All right, so this is a refresher on gravitational potential energy and how to solve some problems with that. Now let's look at Hooke's law, and we'll kind of take a step into our kind of new type of energy that we're looking at this year. Robert Hooke was the one that developed the law for elasticity. This is all about elasticity. And Hooke's law states that the restoring force of a spring is F equals kx, where k is the spring constant. So F is the force, so any force, any spring force that we have is F. That's the force that a spring will provide. And that's equal to a constant, a spring constant, that would be characteristic of a given spring, and x, which is how much you displace or stretch the spring. Okay? So the force that's required to stretch or compress a spring is related to, in a linear fashion, so this is a linear relationship to the distance that you try to stretch or compress it. Okay? Spring force is, as all forces are, a vector. Okay, but it's a vector that acts in a different direction depending on what's happening. So if you stretch a force, if you stretch a spring, it's going to want to return to its original position. If you compress a spring, it's going to want to return to its original position. So the spring force itself, the direction of it, can change depending on what you're doing to it. It's what we call a restoring force. Okay, so it always wants to go back to its equilibrium state. So here's a little example to kind of highlight what we're talking about. We've got a block of mass 4 kilograms, and it's placed next to a spring with a spring constant of 200 newtons per meter on a flat, horizontal, frictionless surface. The block is then pushed against the spring, and it compresses at a distance of 0.05 meters. Find the acceleration of the block just at the instant we release the system. Okay, so this is the instant that it leaves the spring. Let's just alter for a minute, just to make this really clear, the instant it is released. And we'll talk about why this is an important change to make. So here's our block, and we know that it has a mass of 4 kilograms. And we're just going to stretch, we're just going to sketch for a moment our situation where we have this spring, and this spring has of course been compressed by 5 centimeters. Okay? If we were going to draw a free body diagram, we'd of course have the normal force, we'd have the force of gravity, and pushing this out is our spring force. This block isn't going to accelerate up and down, so in this case the normal and gravity are equal. They're opposite in directions, but they would, of course, there would be no acceleration in the y direction. And so what we can begin with is, as we do in the case of all force problems, F net is equal to ma. And in this case, the only force that's acting to create an acceleration in the x direction is the spring force. And so we want to find out, the instant this system is released, what is the force, what's the acceleration of the block. So at the very, very beginning, this problem tells us that we have spring constant times x. And this is, of course, what the spring force is. Okay, the spring force is equal to kx, and this in turn is equal to ma. And if we divide both sides by m, we can see right away that the acceleration is k times x times m. So we've got 200 Newton per meter is our spring force. The initial compression of the spring was 0.05 meters, and the mass was 4 kilograms. This is equal to the acceleration. And when we do this, we get the acceleration is equal to 2.5 meters per second squared, and the direction would be in the same direction as the spring force. And there it is. The reason why this up here was an important thing to clarify is because, of course, the spring force and the acceleration changes with x, because Fs is proportional to how much it's stretched. So when this spring is here, but then at a later time it's gone on and has moved a little bit, now the spring is not coiled up quite as much, and there may still be a spring force acting, but of course when you compare this scenario with this scenario, there's less of a compression here than there is here. And so the spring force changes as, of course, the spring becomes unstretched, which is why we can only calculate accelerations in grade 12. We can only calculate accelerations at a certain instant in time, because that acceleration is always changing, and we just don't have the tools yet mathematically to deal with accelerations that change. So that was an important distinction to make. Moving along, we come to really not just talking about a spring force, but talking about elastic potential energy, because this unit is on energy. So let's talk about elastic potential energy and what we get. There's a really nice way to arrive at this, and it involves creating a graph. And so if we set up our axis, and on one axis we sketch force, and on the other axis we sketch displacement, which is x. In this case we're going to call it x. What we're going to notice is that we get a linear relationship. Okay? If you ever want to know how much work is done in an object, all we need to do is plot a graph of force versus displacement, and the area underneath that graph gives us the work that's done. So in this case, if we have F equals kx, we say that F is our y, and we say that x is, of course, our x, then this very realistically is y equals mx plus b, where this right here is the slope of the line. And we can see that k would be the slope of this line. Okay? What's really nice is that the area that's underneath this curve, this whole area, is known as the work. Okay? So I'm just sketching this in here. This is the work that's done by the spring, compressing it over that distance. So let's take a look at a little derivation, because the graph is great, but we want to turn this into an equation. Work is equal to force times displacement. And in this case, it's the area under the line, or the curve, whatever the case may be, which is a triangle. 1/2 base times height. And here, 1/2, the base is, of course, x, and the height is our spring force. Okay? But we know that the spring force is equal to kx. So we can make this substitution right here, and we can say that the work is equal to 1/2 x times kx. And if we rearrange this, we arrive at elastic potential energy. The energy stored in a spring is 1/2 kx squared. And this will be the formula that we will now go on to use whenever we're talking about the energy that's stored in a spring due to its extension or due to its compression. One final example. A frictionless metal block of mass 5.0 kilograms slides at a speed of 6 meters per second into a fixed spring bumper with a spring constant of 720 newtons per meter. The block eventually comes to rest. How much work does the spring do, and how much does it compress? Okay. So what we've got is we've got a situation where a spring is removing kinetic energy from the system. Okay, so let's make a note about this first. For this system, the kinetic energy of the block okay? The kinetic energy of the block is transferred to the spring. So what I want you to think about, let's talk about what we have. We know the mass of the block is 5.0 kilograms. We know the spring constant is 750 newtons per meter. We know the initial velocity of the block is 6.0 meters per second, and we know the final velocity is 0.0 meters per second because it comes to rest. At the beginning of this lesson, when we were looking at work and when we were looking at kinetic energy, we said, if you can find all the work that's done in an object, that will tell us its change in kinetic energy. So consider this expression right here and try for yourself to determine the answer to these two questions. You will find out when you check your answer that the compression of the spring X is equal to 0.5 meters. So try this question on your own, and we'll take it up in class next day.